In this session, we do something real, in the sense of something in the real world, the hydrogen atom. So our quantum mechanics becomes finally applicable to the real world. We now have enough techniques and theory to start to understand how atoms behave, and start with the simplest atom, which is the hydrogen atom. Now we can't do the full treatment yet. We're just sort of the early stages, the beginning stages, because we haven't yet done the quantum mechanics of angular momentum, which is chapter 7. So we're still in chapter 4. So we still have quite a ways to go. But we have done enough techniques now. We can do the radial r, the radius. We can do the radial part of the hydrogen atom. Now, a hydrogen atom, that's something that exists in a three-dimensional space, right? And up till now, our Schrödinger equation has been limited to one-dimensional space, right? Like d squared by dx squared, one-dimensional. So this time we will generalize the Schrödinger equation to 3 dimensions. So you may notice here, now before we just had d squared by dx squared, one-dimensional Schrödinger equation, but now in 3 dimensions you just generalize this to so your second order differential operator now, instead of just being only d squared by dx squared, it's now d squared by dx squared plus d squared by dy squared plus d squared by dz squared. So you have this sort of 3-dimensional form now for the Schrödinger equation. And this, where does this come from? Well, partly it's like a postulate, it's just assumed to be so. I haven't derived it, but you could probably make out a very similar case to when in earlier lectures I sort of quasi-derived the Schrödinger equation from fairly simple assumptions. You could probably do something similar to here in 3D, 3-dimensional case. But assume for the moment, this is the Schrödinger equation, ST, because again the potential V is still assumed to be independent of time. It doesn't change over time. It's just it depends only on spatial position. But in this case, in this context, this V now, the potential, will depend on position in 3-dimensional space. Right? So this V here is in general a function of x, y, and z. Right? Now you can rewrite this. This is in x, y, z coordinates. Now, there are different ways you can position a point in space. The different coordinate systems. The most common one, I suppose, is just x, y, z. But there's another one called so-called spherical coordinates, where you position a point in space by giving its radius, like I'm trying to visualize here. So here are your XYZ axes, right? Right? Now imagine that you've got a point here, say out here somewhere. So in spherical coordinates, you draw a line between that point and the origin, and that distance is called r. So that's the radius. And then you can use 2 angles, theta and phi, to specify the orientation of this radius going out to that point. So if you know those 2 angles and you know the distance r, so with those 3 coordinates for that point just here, r, theta and phi, you can specify the position of that point, right? So spherical coordinates. Now you could, in terms of spherical coordinates, you can rewrite this operator d squared by dx squared plus d squared dy squared plus d squared dz squared. That sum, that operator, usually goes under the name of the Laplacian, after Laplace, the French mathematician. Okay, so this Another alternative name for it is just del, D-E-L, the del operator. Well, del squared actually. Del squared. Del squared. So it's like a triangle. The triangle is called del, but del squared. And del squared by definition is this. It's the Laplacian. Right? Okay. Now, I'm still debating with myself whether I should teach at least part of an undergrad course on the topic of vector calculus. You know, stuff like grad, which is short for gradient in 3 dimensions, div, which is short for divergence, you know, stream flowing out of a volume, flowing into a volume, you know, and curl. You know, how much does this vector field curl around, or turn, or twist? The del squared operator, this kind of stuff in spherical coordinates. It's so needed. I mean, like, you know, it's cropping up here. Knowledge from vector calculus is needed. So I may give a course on that because it's so useful, and you know, it's sort of like an essential knowledge as background for graduate level stuff. So I may add a course on vector calculus to the undergrad level. Anyway, all right. Now you can rewrite this Laplacian operator, del squared operator, in terms of r, theta, and phi. In other words, using the spherical coordinates. Right? Now, if your potential here, if it is radially symmetric or spherically symmetric, so if it doesn't matter which direction your 2 angles, theta or phi, if your potential is spherically symmetric, so the value of the potential is the same on the surface of a sphere of radius r. So if that potential depends only on r and not on theta and phi, then you can split up this wave function here into 2 terms. A term u that depends on the radius, and another term, let's call it f. Now this is analogous to something we did a few lectures back with respect to position, or x, because 1 dimension, x, and time, t. Right? But if your v is spherically symmetric, you can split this up into these terms. So if you plug that into your psi here, and v is independent of your angles, then you can rewrite this equation in the following form. There'll be an r part, the radius, and you can solve the angle part separately. Now, for the moment, we're just tentatively starting, right? We haven't done angular momentum and so forth yet. But we can start dealing with the radial part of this wave function. See, the function, strictly speaking, depends on 3 variables. You know? The wave functions that you get for the hydrogen atom, some of them are radially symmetric, but others have sort of loops. You know, they depend on the angle, and as you get to higher and higher orbits, you get all these sort of loop. You know, the electrons they're not just sort of going in the probability density of the electrons in the inner orbits. They are spherically symmetric. But the outer ones, you get all these loops and stuff, and it's due to those loops that you can get chemical bonding between atoms. So these loops, where the wave functions are not spherically or radially symmetric, but they depend on the angles. That allows you to get chemical bonds and stuff. So I mean, there's a whole branch of chemistry, if you like, physics, called quantum chemistry, which is the quantum mechanics of the chemical bond. You know, why the hydrogen molecule, so H2, not just H, but H2, why do those two atoms bond together? Why do they stick together? What's going on? Well, to study that stuff, you do quantum chemistry, which is the application of quantum mechanics to the chemical bond. I guess the main guy there, the famous sort of father of quantum chemistry, is Linus Pauling. He got a Nobel Prize, two of them in fact, one in chemistry and the other in peace. He was very active in the anti-nuclear campaign after the end of the Second World War and so on. All right. Okay, so let's now the Laplacian operator. Once you've done enough vector calculus. Now, if you have not done vector calculus, you've got a problem, and I've got a problem. That's why I'm seriously thinking I'm going to have to teach this course. But you have to trust me if you're not familiar with this. You can rewrite the Laplacian, which is of this form, dx squared, d squared by dx squared, blah blah blah, in terms of in spherical coordinates. So in terms of r, the radius, and the two angles theta and phi. Now the radial part, when your v is